Okay, welcome to the session of error correcting coding. And our first presentation today will be error characterization for NAND Flash memory, and the speaker will be Yitzhak from LSI.
Good afternoon, everyone. This is Yitzhak. I'm from DSSC from Carnegie Mellon University, and I work closely with Dr. Erich from LSI Corporation and Professor Xinmiao from Carnegie Mellon University. Today, my topic will be using error characterization for NAND Flash memories. For NAND Flash memory, today we can enjoy like several hundred gigabytes capacity, and the NAND Flash memory capacity will get larger and larger in the near future. And the main technology is due to CMOS scaling and multi-level scaling technologies. But the thing is that when transistor becomes smaller and smaller, and when more bits are programmed per cell, then the reliability becomes an important issue. And we can see that when the flash memory goes from single level cell to multi-level cell and go to 2x nanometer technology, then the error correction capability requirements increase exponentially. But ECC scales very poorly, and it can be expected that it will be very hard to gain required reliability for NAND flash-based products in the near future. So what can we do now? What we can do is that to design more efficient and more reliable error correction codes. But the first step and important step is to that we should understand how the errors of the NAND flash memory looks like. So how can we do that? So we need to set up an experimental platform to testing the flash memory to see how the errors looks like. This is the system infrastructure we build to testing the flash memory. Here is the flash memory. And then we design our own NAND controller in FPGA to read and write and erase the flash memory. And then we have a USB connect to the host machine. And then the host machine stored a bunch of huge data files, and then can be programmed to the flash memory and read out. And the testing technology is that we we set up a given block, and we erase it and continue to program it, and then read data out and do comparison, and then to compare the original data and the read data until we find errors, and then keep on going and to get a significant number of errors. And our platform can support a bunch of flash memories, and in this talk I only show the 5x nanometer SLC technology flash memory as an example in this talk. This is the system platform. This is the HAPS board, and the HAPS board has a bunch of interface to support a bunch of daughter board. And this is the USB daughter board we use to communicate with the host machine. And this is the flash daughter board. And each flash board, this is the USB tag. And then when we program, the files go through from USB to the another FPGA behind this board to go to the NAND controller, and then the NAND controller can write the files into the NAND chips. This is the write path. The read path, the read is similar, but the direction of the path is just in the opposite. So this is our NAND controller implementation, and our NAND controller is different from what you can get from commercial NAND controller. And we can support two modes. One is normal mode, one is acceleration mode. In normal mode is that when we power it on and it will go to the idle state, and then we will do reset, and then each time our NAND controller can execute the command transferred from the host machine, and can do erase. Given me an address, I can do erase a certain block. I can program a given page. I can read a given page out, And we also support an acceleration command. That is, host machine can tell our NAND controller to you do which block you do the testing and how many iterations you did that. And then our NAND controller can execute the command in a batch way from erase, program, read, and do compare. And for using our normal mode, it is kind of slow, but we can get enough data. And using acceleration mode, we can run very fast way. So this is the time we can show that with acceleration mode, we can execute the erase program and read comparison cycles within 5 milliseconds. And with non-acceleration mode, we can run, we should like 100 milliseconds. And then we use the hybrid, use both normal mode and acceleration mode together to get both the detailed and the accurate results. So what the results look like? Here is the error results we see from the very beginning to almost the end of the life. And from this picture, we can see that at the beginning of the lifetime, we didn't see any error at all. And then the error of the flash memory of a given page increase when we do the program erase cycle until to the end. And we can, during its lifetime, we can see that at the beginning, no error correction code is needed at all. And during this stage, we can use just a very simple code for if we, for example, if we apply 32K bit BCH code, we can use a very high coding rate to make the coding very efficient. And then if we go to this range, we can still correctable, but we need a more complex ECC and more powerful ECC BCH code, but the coding rate is lower than previous one. Then eventually, many errors come. It will be very hard to correct. Okay. Means endurance time. Number of cycles to until 14 million cycles.
You wait 14 million cycles, right? But
yeah.
The part when you read the percentage, what is reported there as the endurance of how the part is being sold?
Sorry, I didn't hear.
This part is put in the market with how many cycles guaranteed?
Yeah, it is different from. If we see this, it will be different from what we can see from the data sheet, because there are a bunch of reasons. Like our is testing, our is in lab environment. There is probably in many difficult environment, and then another is that this is another thing that probably the data sheet should be more conservative. They should consider every very tough situations, but this is this results is just in lab environment results. Did I answer your question?
Do you have an idea how much further you went
beyond 40 million cycles?
No, beyond the manufacturer's
Yeah, a lot, but much different from the slot. Because slot is just, if you see from the specification, it only says that given a number of program erase cycles, and then that erase cycle should also guarantee like 10 years. But this is not 10 years. This is just like in seconds level. Number is like 100,000 cycles. Just read and write. We monitor that. Okay, so based on that results, we can do some analysis. So usually in data sheet, people just say that how many program erase cycles can given a certain ECC, and then that will be some metrics, but it cannot tell the whole story. And we can argue that we should use a more accurate definition for effective lifetime. That is how many days or how many how many days the flash memory can tolerate. So this can be another. It has some relationship with the nominal life cycles. It will be that this cycle will multiply the whole storage. The denominator will be the total data will write into the storage, and then this is the average throughput. And we make a simple simplification, assume that the well leveling is ideal, and then there is no right amplification. So based on that, we will see how the error correction codes we needed. And for example, from the data results, we can see that if we want to reach 1 million cycle, then in lab environment, 32K Hamming code should be fine. But if we want to reach 14 million cycles, we need to correct 2,000 of bit errors, and then we need this kind of BCH code. And if we see from the plot, and then if we given us same page length, that is 32K, that will be equal to the page size. And then when the code becomes more complex, sure, we can go, the lifetime will go linearly increase. But this is the nominal lifetime, but the effective lifetime have diminishing returns. We can see that if the coding rate is less than 8/9, it will get diminishing returns. And we found that the 8/9 coding rate should be optimal if we given the length of the BCH codes. And we can see that the errors are highly cycle dependent, and we can also see that the errors are location dependent. And this plot shows the results that we choose one block from the even plane, that we call this even block. And this is the results we choose from the odd plane, that we call odd block. Then they reach the same errors in different program erase cycles. And even inside the same block, different pages have a different total number of errors. And the interesting thing, we can see that this is a very high number of the page. They are more easy to get errors than the other page. Based on that, probably we can use this kind of results to redesign the well leveling algorithms. And we can also see that the errors are asymmetry. And for our flash memory, we found that the error can be defined from 1 to 0 error and 0 to 1 error. And we found that the 0 to 1 error is more dominant. And this is the reason probably is that when we do erase the whole flash memory, then every bit we read out should be 1. But after many cycles, we found that if even we erase the whole block, then we don't write anything out, we read things out, we find that some cells will stack to 0. That means that the cell, after many cycles, program erase cycles, the cell will get erase errors. And we can also see that the errors are also correlated to its neighbors. And we just analyze it. For example, here is one transistor, and then there are 2 transistors on the same word line. And we can see that because these errors are usually from 1 to 0 errors, we can see those two its neighbor values. It can be 0, 0, 0, 1, 1, 0, or 1, 1. And the interesting thing we find that if we see when we find an error locations, and we can find that if both of them are all zeros, the probability is very high, and if both are ones, the probability is low. Then we can, because in our experiment, the flash memory is kind of black box, so we can only guess the reason. So probably one reason is that the bit lines have interference, and then if I both store are 1, then after bit line pre-charge, when I read out, should be 1. But if one of their values are stored as 0, and then because its neighbors are 0, it can drop down the bit line a little bit. If the 2 neighbors are 0, then it will drop down the bit line more. So probably that's why when 2 neighbors are 0, then the cells in the middle will more easily to get errors. And then we also show the error distribution. And this is just one example. We get a bunch of these kind of results. We just show one sample here. And then the x-axis shows that the cell location on the word line, and the y-axis shows that the cells in the bit line, and we can see that the errors are more likely to be clustered in bit line than in word line. So conclusions: we set up a FPGA-based flash testing platform that we can do hybrid error generation to get the errors in much faster way, but does not lose any accuracy. And our platform can also support a wide range of flash memories. And we show one error patterns for 5x nanometer single-level cell flash memory here, and it shows some error patterns. The errors can be cycle-dependent, the error can be location-dependent, and it can be also value-dependent. Based on these error results, we can use these error results to develop some techniques to improve the reliability of NAND Flash-based memories and SSDs. And this is my reference. So if you have any questions, just feel free to ask me. Okay.
So you investigated the correlation of errors among cells which are on the same word line. Have you done a similar experiment when words are on the same bit line rather than word line?
Yeah, we can do that, but we will not show the results here.
Okay.
Then in your error system, you showed 2 pages, the 62, 63, which are bad. The error rate was bad, and other pages were clustered together. It's just artifact of that NAND that you used, right?
Yeah, we are using NAND flash memory.
Yeah, that's right. It's just an artifact of that. I mean, that's what we generally observe that. It's just generally observed that some pages are worse compared to the other page. You saw a lot of clustering for pages, 1 through 62 or something.
Yeah, yeah,
and
yeah.
2 pages were bad. In general, that's what you observed.
Yeah.
Okay.
Select lines. Yeah.
So the effect you saw on a page, variations between the different pages that held across different flash chips and different vendors of chips and different types of flash chips? Or was that a one sample, one vendor, or was it more general?
Means these results?
Yeah, the result were...
There is only one vendor for one certain technology.
Okay, so one vendor, one technology node.
Yeah.
That wasn't a more general, so
Yeah,
we saw that on multiple chips.
Yeah.
Okay.
Can you say anything about the MLC, particularly for the asymmetric errors, if you saw that, or about the cell interference?
We see that. We can see the error symmetry for MLC.
What kind of asymmetry? Can you tell?
It's hard to say because it is not the target for this topic.
Okay, thank you.
Okay, let's thank the speaker again. And our second speaker will be Dr. Bose from Oregon State University. He will talk about some limited magnitude error correcting codes for flash memories.
I need to use my glasses. Thank you. So this talk is in collaboration with Torleiv Klove from University of Bergen and my postdoc Noha from Oregon State University. Okay, first few slides are from Andrew Zhang. He gave me these slides. So you can see the application of flash memories in different units. A typical many of you are familiar, but I just want to briefly explain here. A typical memory unit is something like this. You have a floating gate, and if you want to represent 0, there is no electrons there. And if you want to represent 1s, you inject electrons, so that will form 1 here. Okay. Now, So this is single level. Multi-levels, increase the density. What you do here is, instead of storing zeros and ones, in each cell you have multi-levels, normally 2 or 4 or 8 or 16. Okay. So multi-level has introduced many challenges. The first challenge is because when you have multi-levels, the window is very small. Then what happens is, if you, for a typical example is, if you are 2, the error may go to 1 or it may go to 3. Or it is limited magnitude in this particular case. Okay. So the second problem is programming a particular cell. Programming from 0 to, a lower level to higher level, you can inject electrons, and it may be reasonably easy. But when you want to go from higher level to lower level, say for example, so then you have to erase the whole block of data, normally about 100,000 cells, then you have to reprogram all these things. Okay. So because of this one, it is very expensive, very slow process. Okay, so a typical example, in order to do that one, so we don't want to go beyond certain level. Suppose we want to program at this particular targeted level, so slowly inject electrons, maybe different iterations. Okay, so because of that one, you can see here, so it takes, we don't want to overwrite beyond certain levels, so it takes more time in order to do this one. Okay. So the idea of this one is, so this you can, the idea is using error correcting codes, whether we can improve the speed of this one. So that is what we call as here is asymmetric error. Okay. So if you go to you can think of this one as, if it overwrites, you can think of this as an asymmetric error. So what I mean by asymmetric error is limited magnitude asymmetric error. So there is a left-hand side is normally we call as asymmetric error. It may go from 3 may go to 2, 1 and 0 and all those things. This is what we call asymmetric error. So the limited magnitude is, maybe it may go to only limited magnitude. For example, 3 may go to 2 or 3 may go to 3 itself. 2 may go to 1 and so on like that. Okay. So can we use asymmetric error in order to improve the speed? Okay. So my talk will be something like both for symmetric error and asymmetric error, how to design the codes. Okay. So limited magnitude. Even in coding theory, so this is a new topic. There's no code available designing a limited magnitude error correcting code. So only in the last few years, this topic is there, and a lot of people are working this particular area right now. So the objective here is, so you are designing limited magnitude error. Say for example, the data is 1203. So when you transfer, the error may be 2 may go to 1. You can see this is a single error of limited magnitude 1. Okay. So the code design is, we can think of non-systematic code and systematic code. What I mean by non-systematic code is, so both information symbol and also redundant, both are within one particular word. Okay. So you don't know where the information bits and where the check digits are. Where in the non-systematic code, so the information, you are given information symbols, and I want to append certain check symbols so that I can do the error correction. Okay. From practical point of view, so what we want to do here is, we want to design systematic codes. Okay. So the previous work in this area is, not necessarily related to magnet and flash memories. This was one of the first code design given, in 2004, Ashwood and his group. So designing, correcting all limited magnitude asymmetric error. It is non-systematic code. And then we have given some code, it was published last year, and systematic all error correcting code, limited magnitude. You can correct all the errors. And Shuki Buruk and his group from Caltech, they have designed T asymmetric code, not necessarily all asymmetric code up to T. T may be 1, 2, up to certain value. So this was published in the IEEE Transaction Information Theory last year also. Okay. So what I'm going to present here is limited magnitude single error correcting code, I mean, improving over Shuki's and his group results. Okay. So, for example, let me briefly explain how to design this one. So, normally in coding theory, what you have here is you have a generator matrix and also parity matrix. So, this is a typical parity matrix. So, what it means here is every code word will be orthogonal to this particular vector, this particular matrix. Okay. So, I mean, if you have a code word, when you multiply with the H matrix, H transpose, it will be equal to 0. Okay. So, now I am transferring the data. When you transfer the data, assume that a limited magnitude error occurs, +1 error occurs. That is, we call as E is the error vector. So, then you computed the receiver, you compute the syndrome. When you compute the syndrome, what happens is C times H, C is a code word, it is 0. E times H transpose will be 1 times wherever the particular error occurs in that particular location times the corresponding column vector. So if you look at here, the corresponding columns, so the columns are all distinct. So because of that one, I can do once you get the syndrome gives the corresponding column, from the column I know where the error location is, I can do the error correction. Okay, so that's the idea here. So this is ith column give the portion of the error, I can reduce by 1. Now let's look at here, suppose limited magnitude up to length 2. So it may be it may be +1 or it may be +2. How do you do this one? Okay. Say for example, so this property is useful. For example, if you take 5, the 5 is the, assume that the number of levels. So 2 is a primitive root of 5. What I mean by primitive root of 5 is when you take the powers of 2, 2 power 0 mod 5, it is 1, 2 power 1 is 2, 2 power 2 is 4, and 2 power 3 is 8 mod 5 is 3. Okay. So it generates all the integers between 1 and 3, in this case 1 and 4, all the elements here. Then how do you construct the H matrix is, this is the parity matrix. So how do you do here is, the first non-zero, okay, so the first non-zero vector will be either 1 or 4 and all the combinations here. For example, 0, 1 and 0, 4. So if the first non-zero element is 1, and the first non-zero element is 4, and then 1 with all the combinations here, 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, and 4 with all combinations, 4, 0 all the way up to 4, 1. Okay. Suppose if you choose this as the H matrix, so then how do you do the error correction? Let's assume, okay, so error correction is C is a code word and E is the error vector. So when you multiply, you get the syndrome as S1 and S0. Okay. So the first, okay, if it is a single error, what happens is 1 times the particular column. Okay, so what you get here is L is, when you multiply the corresponding column, it will be the first non-zero element will be either 1 or it will be 4. Okay, so then I know it is exactly single error, limited magnitude 1. If it is length is 2, so then when you multiply 2 times the corresponding column, so because the first non-zero element is 1 or 4, 2 times 1 will be 2 or 2 times 4 will be 8, 8 is equal to 3. Okay. So from that on, I know exactly there are error vector is the number of error. Now in this case, magnitude is 2, and I can do the error correction. Okay. So this gives an idea of how I am going to construct the code. So in general case here is this is related to what is called modular sequence. Okay. So, this is from the number 3 concept, it comes here. You choose the corresponding H columns. All these columns are what we call as modular sequence. So, the first non-zero element is correspond to what is called the B sequence. So, in general, what is a modular sequence is, you choose all these numbers, B0, B1 up to Bm minus 1. When you multiply to say, A times B, these are all distinct. So in this case, A is, in our case, it is limited magnitude. It may be L means 1, 2, 3 up to L minus 1, up to L here. Okay. So L is 0 from, okay. So this is the modular sequence one is this exactly. If you take Q is equal to 4, the modular sequence, I can choose 1, 2, 3. This same as single error correcting code. And Q is equal to 5, modular sequence for B02 is 1, 4 or 2, 4, just like what I explained before. In general, what you do here is, if it is Q is a prime number, you choose this B sequence as every powers of 2. I mean, even powers of 2. 2 power 0, 2 power 4, 2, 2 power 4, all the way up to 2 power Q minus 2. Okay. So by doing this one, what happens is when you have single error occurs, it is exactly 2 power even number. If it is double error occurs, 2 power odd number. So that's the idea here. Similarly, for Q is equal to, I mean, if Q is a prime number, 3 is a primitive root, I can do up to 3 error, up to limited magnitude 3. So this is the scheme you can explain here. Okay. So in general, what we have given here is in the paper. Okay, you can think of this one as Q is equal to some power P times L plus 1. Then we can find out the P sequence. How you are choosing this one is, you choose the B sequence as Bi is equal to I times L plus 1. Okay. So when you choose all these things, then you can construct the H matrix. So by choosing the H matrix, then I can do the error correction. I don't want to go details are given in the paper. You can look at that. So in fact, so the length of the, if you are R check bits, we can have almost like the length of the code will be almost like M times Q power R minus 1 over Q minus 1. And it can correct limited magnitude of any length L here. Okay. So and then we can prove this is optimal. So in the sense, in order to choose the maximum number of code words, you can go through the proof here. The maximum number of code words, if it is level, if you are using Q is the number of levels, it is Q power, and you are using N is the length of the code word, then it is the maximum number of code word can be at most Q power N divided by 1 plus N times L. So using this scheme, we can easily prove whatever the code we have given for L is equal to 1, 2, 3, it is optimal code. It is, you cannot do better than this one. And for general case, L is greater than or equal to 4, the code gives the close to optimal code. Okay. Now we can extend the results for even for symmetric error correcting code also. So in this particular case, let me briefly explain this one. Okay. So L is equal to 1. This is known in coding theory what is called a lead distance code. Okay. So in the case of lead distance code, if you choose, in this particular case, what you do here is you choose the H matrix, something like that. In this case, the leading non-zero term is, Q is equal to 5, either 1 or 2. Okay. So whenever single error occurs, plus 1 error occurs, you get the corresponding column. 1 and also the whatever the value here, or 2 and some other value. And if it is negative error, minus 1 error occurs, actually it is minus, the leading non-zero term will be minus 1 or minus 2. Minus 1 is same as 4, minus 2 is same as 3. Okay. So from there, you can easily find out whether it is plus 1 error or minus 1 error. Okay. In fact, this will be much better than whatever the code given by, you can use the Hamming code and use the gray mapping, and then you can construct the code. In fact, this code gives much better information rate than the Hamming code or using the gray code mapping. And in general also, if you want to limited magnitude plus or minus L, then I can use the what is called B1 minus L sequence. By using this particular sequence, the sequence is similar to what I have given in the previous part. So in this case, how do you consider the B sequence is I times 2L plus 1 instead of I times L plus 1 for L is in that particular, I is in that particular range. Okay. By using this one, I can do limited magnitude error correcting code, symmetric error correcting code, and these are close to optimal also. The summary is based on the B sequence, we can construct limited magnitude error correcting codes. And quotes are optimal or close to optimal. And many of the results are given in this paper. It will appear in IEEE Transaction Information Theory soon. Thank you.
Are there questions? Okay, I have one.
Okay.
So, could you explain how the decoding can be done by using this code you proposed?
So the decoding is similar to the Hamming code, what you do here. So you look at the syndrome, so H matrix, whatever the syndrome, from the H matrix you can construct the syndrome tree. Okay, so in this case you have to do mod operation instead of, in the case of Hamming code, what you do here is exclusive tree here. So in this case, whatever the base number of levels, you use addition mod Q, and you construct that one, and then you can find out the syndrome. From the syndrome, you can do the error correction.
Okay, so basically, it's single error correcting code.
This one is basically single error correcting code. Okay.
Have you extended to multi-error correcting?
Shuki Brook and they have given the multi-error correcting code, and we have some results. We have not, so still working on some other things here.
Okay, let's thank the speaker.
Thank you.
Sorry, there's another question.
Oh, I'm sorry. Yeah.
Soft decoding algorithm.
No, I have not done any work on that.
Okay, thank you. Okay, the third talk in this session is error correction scheme for constrained intercell coupling flash memory, and the speaker will be Amit Berman from Israel Institute of Technology.
Thank you all for coming. I'm very excited to be here. I'll talk about error correction scheme for constrained intercell interference in flash memory. So first, I'm going to review some background about the intercell coupling. I'm going to review the constraint coding approach and the error correction scheme for the constraint coding, give an example, and conclude. Okay, so let's get started. The floating gate to floating gate intercell coupling causes the charge in one cell to affect the neighbor cell. Threshold voltage means interference. This coupling shifts the threshold voltage by a degree that depends on the level of coupling between the adjacent cells and on the amount of charge in the surrounding cells. We can see in the picture a simulation showing the intercell interference, effect. We have an accurate model for the intercell coupling. The interference is actually deterministic, as you can see. By knowing the voltages of the neighbors and the intercell capacitance, we can accurately calculate the impact on the voltage of our current floating gate transistor. When we do program and verify, charge is added to a cell in small increments. The VT is checked after each addition, and the program ceases upon reaching the desired voltage threshold. Therefore, the voltage threshold of any given cell is affected only by charge changes made to its neighbors after its own charging has been completed. We conclude that the degree of intercell interference depends on the programming scheme. There is some existing interference mitigation techniques. The first one is proportional programming. It uses concurrent incremental programming of all cells tailored for near simultaneous completion. It is insensitive to coupling parameters and has a simple read, but it's complicated possibly slow programming, and can account for next line. The intelligent redecoding, based on programming order with a successive decoding interface cancellation. It's a simple programming, but you must know the coupling parameters. There's no variation allowed. It results in a complex, slow read. Our previous work described the constraint coding, which I will describe in the next slide. The approach of the constraint coding is to forbid those adjacent cell charge combinations that result in the greatest threshold voltage shifts. This results in narrower distributions, and additional charge level can be added, which results in high capacity. But we have code rate lower than 1, which means lower per level capacity. The capacity is maximized via the optimal trade-off. The basic framework is as follows. Given the programming order, we express the change to the cell's VT as a function of the charge level of its neighboring cells. We refer to this function as the Intercell Interference Severity function, DC. The program data is constrained according to a predefined constraint referred as T, such that for every cell, C, the DC is smaller or equal to T. Example for this can be shown in the breadth-first programming order. Breadth-first is when you have one-dimensional single row of cells, and you have all cells that need to be programmed to a level higher than 0 are first programmed to level 1. Next, all cells which need to be programmed to a level higher than 1 are programmed to level 2, and so on. The intercell interference severity function is the sum of positive differences between the neighbors to the cell C, which we can see as described. And we want to constrain this function to be smaller than or equal to T. T represents a trade-off. Large T is efficient coding, but wider distributions at fewer levels. And smaller T is vice versa. We can see an example of the encoding scheme for one-dimensional 8 levels per cell, and T equals 13. We can look at the graph. This is the constraint language graph. It means that traversing the graph edges will generate legal code words. For every cell in this language, the DC will be smaller or equal to 13. In this language, the legal words do not contain the sequence 707. The capacity is 2.99. Transferring it to binary alphabet, we have code rate of 0.99. And encoder and decoder at the rate P over Q can be obtained by raising the graph in the power of Q, removing redundant edges, and using the state splitting algorithm as necessary. We want to treat error handling in the constraint coding scheme described. Our focus here is on decoding algorithms for the case that an illegal code word was read due to errors induced by retention problems. The retention errors are due to charge leakage from the floating gate. They are unidirectional towards the erased level, as shown above. Illegal code words resulting from a retention-related error correspond to situations in which DC is larger than T for at least one cell. Assuming one such error, detected by noticing that DC is larger than T, it is most likely that the error is a result of the charge leakage from the cell C itself, as charge leakage from a neighbor cell would usually reduce DC, resulting in a illegal code word. This also works for multiple such errors in distant cells. The error correction is simply decode C+1 instead of C, where DC is larger than T. So the constraint intercell interference coding can be used to detect and correct retention errors. Every constraint coding has its embedded ability to detect incorrect errors. However, many retention errors do not cause illegal code word read. We can see in the picture a small fraction of all retention-induced errors node words. Only a small fraction is illegal code words. So can we do better? And here I'd like to quote Einstein saying that if the facts don't fit the theory, change the facts. So what do I mean in this context? Instead of trying to find a code to fit the flash, try to do the opposite. If our code doesn't fit the flash, let's change the flash in order for it to fit the code. How can we do that? Let's examine the case of code words of length 3. We observed that illegal code words contain the sequences L1, 0, L2, L1, 1, L2, and so on, according to the constraint T. The first sequence has the largest number of illegal code words. The second has the largest number is the second sequence, and so on. Therefore, if we change the flash memory channel such that the error probabilities will be as shown above, well, the highest error probability is from level 1 to level 0, would increase the probability that a retention error will cause a correctable illegal code word read. This modification can be made by an equal allocation of read margins between adjacent cells, so that lower levels have smaller margins than higher ones. Next thing we can do is to add constraints. Legal code words are constrained to be offsets of legal words. For example, for L equals 7 and T equals 13, the language is constrained such that the sequence 717 is the only sequence in the form of L1, 1, L2. Therefore, charge leakage from level 1 to level 0 would necessarily lead to 707, would necessarily lead to illegal code word. This reduces the language capacity from 0.99 to 0.93. We can see the constraint language graph as shown above, and generating encoder and decoder from this language graph as was written before. If we have multiple errors, we can use iterative decoding. In the event of multiple errors during read, means multiple cells in which DC larger than T, the decoding scheme first focuses on the cell with the most higher level neighbors and corrects it. The process is then repeated until legal code word is reached. If the errors are sufficiently far apart, means distance of 2 cells at least, in this example, they are simply independent and can be treated as a single errors. So, for conclusions, constrained intercell interference coding can be used to detect and correct retention errors. The errors of low program levels can be detected at read due to violation of constraint coding restrictions. As the constraint T tightened, the probability to capture and correct retention errors increases. However, lower T also reduces the language capacity. We can increase the probability to capture and correct retention error by using 2 methods. Change the flash read channel by reducing the error rates of higher levels at the cost of increasing the error rates of lower ones. And we can add constraints as necessary. This concludes my talk. Thank you for listening. Yes, please.
For the 3 bits per cell example that you have, if I want to decode any page, I need the information from, for this 3 bits per cell example, if I want to decode, say, upper page, middle page, lower page, I'll need information about all the other pages also because I need level information, right? Isn't that going to add to the latency? I mean, my read time is going to drop. It's going to go up.
If you're using one-dimensional coding, you'll read the page at once, because the flash structure, at least NAND Flash structure, is that you read a bunch of bits at once. And you already have the the levels of the neighbors while reading. If you're using NOR Flash, this also applies to NOR Flash actually. And other non-volatile memories, you do read a bunch of bits, so you know the levels of the neighbors in advance before decoding.
I think, say I'm reading just the lower page, right? So I'll apply a reference in the center, and then I'll get zeros and ones. But if I want to do constraint decoding, I need level information, which is not there when I do the
Right.
page. So
Right. You need level information to decode. If you use only one reference, in your question, you're referring that you have only one reference.
yeah, that's
Right. In this case, you will need more references.
Also, how is the error propagation? Because you don't have only these errors, you also have other errors, right? Your level has this distribution, so it's not that you just have errors of the type that you mentioned. It's actually a AWGN distribution around the mean.
Yes, there are further other methods to combine error correction in the constraint coding. One of them is enlarging the hamming distance between words. When you're using constraint coding, you can just increase the hamming distance between words in addition to this. And this would reduce your code rate in the expense of correcting such errors to reach such bit error rate as you desire.
Thanks.
What kind of method did you use to design the constraint code?
Sorry,
What kind of method did you use to design the constraint code?
what kind of?
Method. Is it based on finite state encoding method? Based on any kind of other method?
It's based on block coding.
Oh, it's block code.
Yes.
Okay, I
It's
see.
it's an constant rate, P over Q.
Okay. And what is the typical code word length of the constraint code? For example, for a given t of equal to 13.
Some experiments we made are, for example, 9 over 10 results in code rate of 0.9. And there are also, if you want to reach 0.99, 99 over 100 cells. In one read, we can read 256 words in parallel. So we restrict our code rate for those, our block length to the amount of words you can read in one time, in parallel.
Okay. Another question is that you have already computed the capacity of the corresponding constraint code. May I know for your practical code you designed, what is the corresponding encoding efficiency?
You can reach the language capacity.
Reach.
Yeah.
You mean reach the efficiency? The coding efficiency is 100%.
Yes, the coding efficiency can be met by 100%, although consider that your decoding complexity and encoding complexity will grow as you reach the capacity. As you address lower capacities, probably your code word would be shorter, and therefore the overhead, the hardware overhead needed to be encoding and decoding would be smaller, resulting in lower latencies. So this might strike a good balance between the latency, the overhead latency of the hardware, and the additional capacity needed to implement those techniques.
Okay, thank you.
Do I have still time for one more question?
Sure.
Okay. So I have a question about the interference model. Could you please go to that slide? Yes, this is the one. So basically it says that if the nearby cells level increased by V, then for the cell in the middle, it increased by C times V. And I was wondering, this interference must be a random variable. So what's its distribution like? Is it centered around C times V, or is it somewhere in between 0 and C times V? In other words, is C times V the central, the mean value, or is it the upper bound?
when you're talking about C, this is actually a deterministic, describing the interference effect. But C has process variations. So you can treat C as a random signal. And there, if C is distributed in a Gaussian distribution, this would have been like, as you described, you can see this drift of level to be Gaussian, except for the highest level, which is not affected.
Okay, thanks.
Thank you.
The last talk in this session is Adaptive Endurance Coding for NAND Flash, and the speaker will be Ashish Jagmohan from IBM.
So I'm Ashish Jagmohan. I'll be talking today about a simple coding technique that has the potential to improve the endurance of NAND Flash. We call it adaptive endurance coding. This is joint work with Michele, Franceschini, Louis Lastras, and John Caridis at the IBM T.J. Watson Research Center. And as I speak, if you have any questions, please feel free to interrupt me and ask. So I think, as is very clear to pretty much everyone in the audience here, NAND Flash has severely limited endurance, and this limited endurance is a fundamental bottleneck in the use of NAND Flash devices. So the latest MLC devices that have 2 bits per cell, have an endurance of somewhere between 3,000 and 10,000 program erase cycles. So you use a device for 3,000 to 10,000 cycles, and the error rate is very high after that. There is a downward trend, both within a density, within a fixed density, and certainly across densities. So TLC devices that have 3 bits per cell, are expected to provide only 1,000 program array cycles, and 4-level devices are expected to provide an even smaller number. While this is good enough for many consumer applications, most consumer applications, this does constrain the use of NAND Flash in many enterprise applications. And enterprise applications, of course, is what IBM is concerned with. So before I describe what we are going to do about it, we should quickly go through what the basic underlying mechanisms of this limited endurance are. So we all know that the way that you store information in a NAND Flash cell is that you transfer charge from the body to the floating gate of a transistor. And the floating gate and the body are separated by a layer of tunnel oxide, which is supposed to be an insulator. So the main mechanism of charge transfer, both in the program and erase steps, is something called Fowler-Nordheim current injection. And essentially, the point is that every time there's Fowler-Nordheim current injection through this tunnel oxide, there is a stress induced on the tunnel oxide, and that leads to degradation and trap generation in the tunnel oxide. So these phenomena, tunnel oxide degradation and trap generation, lead to an increase both in the write raw bit error rate. By write raw bit error rate, I mean the bit error rate that you measure immediately after writing to the flash, as well as the retention raw bit error rate, which is the raw bit error rate that you see after, say, a retention of a few months. And there are several phenomena which lead to this. They're called charge trap conduction, there's charge detrapping, there's stress-induced leakage current. There's a lot of literature about these things. And well, of course, once the raw bit error rate exceeds a certain rate and it exceeds the correction capability of the ECC that you're using, you have page and sector failures, and your flash device, your flash page, sector, block device become unusable. So now, from the perspective of storage capacity, there's 2 parameters that we can use to characterize a NAND Flash device. There's instantaneous capacity and there's lifetime capacity. So instantaneous capacity is the maximum amount of information that I can put on a device at a given point in time. And wear leveling techniques, for example, try to preserve instantaneous capacity. So they try to ensure that you don't have block failures for as long a time as possible. The lifetime capacity is the total amount of data that I can store over the lifetime of the flash device. And the point of endurance coding will be that we'll aim to increase the lifetime capacity. In particular, we'll try to increase lifetime capacity at the expense of reducing the instantaneous capacity. So we'll try and trade off the instantaneous capacity and the lifetime capacity. So the hypotheses on which this idea is based is the following. A cell's tunnel oxide degradation during a program erase cycle is dependent on the level programmed on the cell. In other words, the way that you induce on a cell is data dependent. And the motivation behind this hypothesis is that, well, we expect the Fowler-Nordheim tunneling current to be level dependent and hence data dependent. So for example, if you had two SLC cells, cell A and cell B, imagine that you program cell A to, these are both SLC cells, so you program cell A to 0, which is the program level, and you left cell B program, and you programmed cell B to 1, which is the erase level, and then you erase both cells. You'd imagine that you'd hope, or well, you'd expect, I guess, that cell A would undergo a larger Fowler-Nordheim current injection than cell B. Hence, you would expect that cell A would suffer greater degradation than cell B. So similarly, in MLC Flash, you have different program levels, and you'd expect that different program levels would cause different current injections, and this thus would cause different amounts of wear. So first, we try and verify this endurance coding hypothesis through some simple experiments on devices. So this is what we do. We take a device. This is actually an MLC device, which you're using in SLC mode by only programming half the pages. And the test that we do is that we partition the device into two sets of blocks. On the first set of blocks, we repeatedly program all zeros, and then we erase those blocks. And we do this repeatedly. And every so often, we program a pseudo-random data pattern and read that pseudo-random data pattern to measure the raw bit error rate that we are seeing. And we track the evolution of this right raw bit error rate, the raw bit error rate we are seeing immediately after programming. We track this across time, as a function of the PE cycling. And similarly, on the second set of blocks, we program every cell on the block with a 1 and erase. And we do this repeatedly. And periodically, we'll program a pseudo-random data pattern, measure the right raw bit error rate. And just for reference, the conditions under which this is done, this is room temperature cycling. The cycle time is on the order of seconds. So the dwell time is on the order of seconds. And as you can see, there is a clear distinction between the cells on which you programmed, the blocks on which you programmed all zeros, and the blocks on which you programmed all ones. Similarly, there's some experiments here on MLC. So these are two different MLC devices. These are the 4 program levels that you can program on the MLC cells. We partition the MLC devices into 4 sets of blocks. On each set of blocks, we put a fixed level, repeatedly erase, do this repeatedly, periodically program a pseudo-random pattern. So 2 things stand out. The first thing is that there is, in fact, a difference between the levels. So if there are certain levels, for example, the level 1.1 seems to be distinctly better than all the levels. On this device, the level 1.0 seems to be better than these two, significantly better than these 2 levels as well. Note that this is a bit error rate curve, which is in the log scale. The other thing that stands out, that this behavior is in fact device dependent. And here I'll add a caveat. These are very preliminary results. We've taken a small number of devices. We've taken a small number of chips for each device type. And we've taken a small number of blocks for each chip for each device type. So these are extremely preliminary experiments. I'll also add the following caveat. We have, in fact, recently tested some devices on which you do not see a differentiation between the levels. So it seems like with everything about Flash, there are certain devices that exhibit this. There are other devices that do not exhibit this. So if we had devices like the ones that I've shown you, the idea that we have is the endurance coding idea then is very simple. The endurance coding idea is that you give me data to write. Well, before writing it, I convert it into bit patterns which cause minimal wear. So I know certain levels wear more than other levels. I convert that data into a form which has a small number of levels of the type which cause wear. We call it endurance coding. This is actually a term borrowed from a prior paper in which we investigated how to improve the endurance of PCM. This exploits the level dependence of wear. It leads, in general, to an expansion in the physical data block length. And that is what I meant when I said that endurance coding, what we're trying to do is that we're going to be trading off instantaneous capacity for lifetime capacity. And it is related to a certain area in information theory, the right efficient memory coding problems and problems of that nature. So as a simple example, if you consider an SLC NAND Flash, where let's say programming a level 1 causes you no wear at all, because it's just an erase, and programming a level 0 causes you a certain amount of degradation, then let's assume that you have 4 bits of data to store. By expanding these 4 bits into 6 bits, you can reduce both the average and the maximum number of zeros that you ever end up writing to that device. So you've traded off instantaneous capacity because you could, you've traded off by a factor of 1.5, but you have improved the lifetime capacity. And we'll get into more details of this in the next few slides. So, well, the obvious question is, what is the trade-off between instantaneous and lifetime capacity? So there's a couple of ways that we've tried to, again, come up with preliminary answers to this question. The first way is that we just have a toy abstraction. This is a very, very simplified toy abstraction. Let's assume that you have a memory which supports L levels. Associate level I with a wear cost Ci. And then let's make a bunch of very unrealistic, very simple assumptions. Let's assume that the wear on the cells is independent. Let's assume that the wear on the cells is additive over cycles. In that case, if you denote by F the data expansion factor, in other words, how much of instantaneous capacity are you willing to give up, then you can compute the distribution of level frequencies, which minimizes the average wear cost. And this is a very simple, a very trivial optimization problem. So you can come up with a distribution of level frequencies, which minimizes the average wear cost. And just to demonstrate with some toy examples, this is, if you had an SLC device where the erase level had 0 wear cost, if you programmed a 1, it didn't cause any wear at all, while if you programmed a 0, it cost you some wear. This graph essentially shows you the endurance gain and the lifetime capacity gain that you could get. So if you just look at lifetime capacity, with the data expansion factor of 2, you get a total lifetime capacity gain of 2.4. It's 2.5 for this case, for the MLC case. So for MLC, similarly, if you assume that the erase level had 0 cost and the other levels had linearly increasing cost, you roughly get a factor of about 2.5 in lifetime capacity by sacrificing about a factor of 2 in instantaneous capacity. Okay, so there's a couple of things then that we should look at. First of all, how do you implement endurance coding in practice? Well, a simple way of implementing endurance coding in practice is by the use of enumerative codes. Essentially, you have a table. You list all the sequences with a good distribution of levels, a distribution of levels that doesn't hurt your device too much, and you index into this table using the input data word. And there are there are techniques well-known techniques for this in the information theory literature. However, if you want really low complexity endurance coding, what you can do is that you can use a lookup table with very short block length enumerative codes. So you could say that you have an enumerative code of, say, length 16 bits, and you can implement the enumerative code simply as a lookup table. So you get data, you have a lookup table stored in DRAM, you use the data to index it, you get the code word from the table. By the way, this 16-bit binary enumerative code doesn't do too badly for most data expansion lengths. So this is the theoretical bound. This is the performance that you get with a 2-byte code, with a 16-bit code for an SLC device. So, okay. So adaptive, so there are some system-level issues here. In particular, the point with endurance coding is that you have expanded your data block length. Now assume that you're in a system in which your logical block length is 4 kilobytes, and your flash device has 4 kilobytes physical pages. If you take your 4 kilobyte logical pages and you expand them, then essentially what you're doing is that you're taking a logical page and you're striping it across multiple physical pages. That has a problem. The problem, well, you're increasing the latency. To read that page, you're going to have to read 2 physical pages. So the idea behind adaptive endurance coding, and that's another simple idea, is simply that you do lossless compression of data first, if your data is compressible, and then you adapt your endurance code, the expansion that your endurance coding causes, you adapt that to the level of compressibility so that your code word is guaranteed to fit inside a physical page. So essentially, I do lossless compression, that compresses the data, then I re-expand it using endurance coding, and then I re-expand it to the extent that the endurance coding code word can be written inside of one physical page. So that's basically the idea behind adaptive endurance coding. And now I'll finish off with some empirical verification that we've done. Again, this is very preliminary testing. The following is what we've done. We've taken 2 MLC devices from different manufacturers. There are 3 sets of blocks on each of these devices. We tried 3 different coding techniques. In the first device, the first set of blocks is the baseline block. On the baseline block, we put pseudo-random data. So it's essentially 50% zeros, 50% ones, pseudo-random data. On the second set of blocks, we put endurance-coded data on both the LSP and the MSP pages using the short block enumerative code it's actually just a 1-byte enumerative code with a rate of 0.4. On the third set of blocks, we put pseudo-random data on the LSPs, and we put the endurance-coded words on the MSPs. And we perform two types of tests. The first test that we perform is that we do PE cycling. So we cycle it repeatedly, and we measure the raw bit error rate that we get. The second type of test that we do is retention testing. So essentially, we take a device, we cycle it to 3,000, 5,000 cycles, and then we do thermally accelerated retention testing. We put the device in an oven, periodically take it out, and look at the raw bit error rate. So let's look at first the right raw bit error rate. So this is the first device. The black curve is what you get with pseudo-random data. So if I use the device normally, this is the curve that I would get. This, by the way, is a device that has, I believe, a rated specification of 10,000 cycles. It's either 5,000 or 10,000. So the black curve is pseudo-random data. The blue curve is what you get when you write endurance-coded data on both the LSP and the MSP. And the red curve is what you get if you just write endurance-coded data on the MSP. So the only point of the red curve is actually to show that on this device, and actually on this device as well, you only really need to do endurance coding for half the pages. On the LSPs, you can just write normally. So for both devices, endurance coding seems to lead to a significant increase in lifetime. Where we call a significant increase in lifetime, we measure that by taking a particular bit error rate and looking at after how many cycles the black curve reaches that error rate, and after how many cycles the blue curve reaches that error rate. This is actually slightly inexact because you're actually using different block lengths for the two. You've sacrificed some instantaneous capacity in the blue case. So these are two devices on which you can see the right raw bit error rate. This is an experiment with retention raw bit error rate. I won't get into details except to note the following. For the retention case, so essentially we had 3 sets of blocks. We did endurance coding, and we did pseudo-random coding, and then we did retention testing. 700 minutes corresponds to 1 year of retention. In this case, the increase in lifetime that we got is only 1.7x. So in fact, the lifetime capacity that you get is actually smaller with endurance coding. So essentially, there is a sweet spot. Immediately after programming, you get a huge increase in lifetime. After an year of retention, you just about break even. There's a sweet spot in which endurance coding works. And then there is a device-level simulation, which I will skip except to point out in the results. So we assume that you have a certain kind of compressible data, and we do adaptive endurance coding. And then essentially here, this is a simulation. These are not empirical. This is not done on an actual SSD. Here, I plot the gain that you get in endurance using ideal adaptive endurance coding, an 8-bit, a 16-bit, and a 24-bit code, and what you would get if you only used compression. And the point of this is essentially just to show you that there is, in fact, a significant gap between what you could get ideally and what you get with the 8, 16, and 24-bit enumerative codes. So there does seem to be space here to design good adaptive endurance codes. So the problem of designing a good practical adaptive endurance code is an open problem. Yes? Could you say that again? If you get what?
When you get your errors, you have to compress the data. Does it multiply the number of errors?
No. So for all the empirical results that I've shown you, there's no compression in the picture. So it's not as if you're compressing, then uncompressing, and then looking at the errors. In this case, for the simulation case, a bit error is a bit error. So compression does not magnify the bit errors. So I'll conclude with some remarks. We presented some basic ideas, some basic experimental results underlying the use of coding to improve NAND flash endurance. There are several things that remain to be investigated. There needs to be a much more detailed device-level simulation and empirical verification. There needs to be a detailed quantification and modeling of the effects of endurance coding on write and retention raw bit error rate as a function of different expansion factors in PE cycles. And of course, on more devices, more chips, more blocks. And the design of a computationally simple high-performance endurance code for SLC and MLC NAND flash is unknown to me. So the best that we've done is just simple enumerative codes. Thank you. This one, right?
So you say, oh, there's a gap between teal and black, between the AEC with 24 bits and the ideal AEC.
Yes.
That's with the compression. I mean, I'm wondering about your ideal curve. Is your ideal curve taking into account the fact that the compression couldn't always compress it very much, and therefore you're left with really no room to do much endurance coding in some cases?
So the way that this curve is computed is the following. We have a bunch of 4 kilobyte pages, and each page has a different compressibility. I take a page, I compress it. However much I get from the compression, I re-expand using a different rate endurance code so that it fits inside the page.
Exactly.
Right. So, and you compute the where based on the number of zeros that you ended up writing.
So my question is, does your ideal curve, the black curve, take into account the fact that on some of the pages you just didn't, maybe there are pages where you couldn't do any endurance coding at all?
Absolutely. Because on those pages you could not do endurance coding, and so the number of zeros that you'll end up writing is pretty much 50%.
Yeah, okay.
Yes.
You mentioned on one of the earlier slides that on some NAND chips you observed that there were differences in endurance based on whether you program zeros or ones, and then on other devices you tried, you didn't see that.
There is one specific device that we tested on which there was absolutely no difference between the 4 levels, to the extent that even if you took that device and just erased repeatedly, you would get exactly the same bit error rate as you got with any of the levels.
Right. And so my question is, were you able to find out, is that because they were doing symbol scrambling in the NAND controller, or was that actually a physical property?
So that is a very good question. We thought about symbol scrambling. The reason that we think that there is no symbol scrambling is because even if you just repeatedly erase that chip, you're not writing anything, so there's no scrambling going on. Even if you just repeatedly erase that chip, you get a particular bit error rate, which is the same as, well, it's slightly lower, but not significantly lower than when you were writing to that device.
And do you have a sense of the amount of damage that's done by programs versus erasing?
So again, you could do this experiment. That experiment. You could do that experiment, and you could produce a curve which is just erases, not even writing 1-1, right? So yeah, we do have results on that, and for most devices, the all erase curve is below these 4 levels. However, it is not true that just repeatedly erasing does not cause any damage. It definitely does cause some damage. Yes.
You didn't talk of decoding and the error propagation effectively.
So that's a good question. So it is possible, of course, to design, since we're using extremely short enumerative codes. So we're using a 16-bit code. We're taking 16 bits, we're taking a certain number of bits, less than 16 bits, converting them into 16 bits. It's actually fairly simple to design block codes with non-binary block codes that prevent error propagation between symbols. So your symbol size is just 16 bits. You have a small block, you take it to 16 bits, and you write that. Now, the only thing you want to do is that you want to avoid error propagation between 16-bit symbols. It's fairly easy to design codes that allow you to do that.
Because the rates are pretty low, you want to put a high rate so to compute the capacity and look at this problem like the constraint code problem itself.
So we've definitely not tried to design capacity achieving ECC codes or anything of that nature.